Good afternoon, Year 12. I've made this booklet of questions called a mastery booklet, and the questions will cover the waves topic. And they are slightly more challenging questions. They range from a grade B to A star. And this isn't a video giving you the solutions, it's just giving you a guide to each question, suggesting how you might tackle it. So let's start with the first one. And what we've got is a ripple tank. So you've got a piece of wood acting as a dipper connected to a signal generator, so it's vibrating up and down, and this tray is full of water, and so when the dipper hits the water it will create waves, and the shadows of those waves are projected on the screen on the floor. And I've shown you a similar version of a ripple tank, a smaller version, during lessons, but you can see the wave pattern on the floor. And the student, she finds the total distance between the first and last of 10 shadow lines is 27 centimeters. So basically these are the shadow lines that are on the floor, and the gap between two consecutive shadow lines will give you the wavelength of those waves. And we can use the equation speed of a wave is equal to frequency times wavelength. So the wavelength and the frequency are not given directly, but you've got enough information in that question to calculate the speed of the wave. So a little bit more challenging use of that equation. And part B, so the student suggests moving the lamp to the side of the tank so that it is projecting at an angle, so it's perpendicular to the water at the moment, and she's suggesting that if you move it at an angle it would give clearer waves. So the question is, why should she not do this? So what do you think that the shadow pattern would look like if she moved the wave at an angle? So at the moment it's pointing downwards, and she's suggesting to point at an angle. So I won't give you any further help with that one, but just to clarify what that question is asking. So the student in part C replaces the lamp with a stroboscope. So in this case the light will be flashing at a certain frequency. So as it says, a stroboscope flashes a bright light at regular time intervals. And she adjusts the time intervals so the ripples appear to not be moving. And that's very similar to what we did with the standing wave experiment, where we made that piece of string look like it was stationary, that it wasn't moving. So give the shortest possible time interval that could be used by the student to achieve this effect. So if we consider our shadow lines, and this shadow line will be moving in that direction, and if the time taken for this wave to move from here to here is equal to the time taken for the light to flash, so it flashes here and then it flashes again, if those two times are equal, if the time in between the flashes is equal to the time it takes this shadow line to travel to that point, then the wave pattern will appear to be stationary. And you need to use the information that you were given at the start to calculate what that time actually is. So just a little bit of thought required there on that one. And question 2, now this is all about electromagnetic waves and polarization, and part A should be quite straightforward. I don't think I need to give you any help with that one. And suggest with reasons, part B, a suitable type of electromagnetic radiation to communicate with the satellite. So you've got 7 different types of wave on the electromagnetic spectrum, and we're trying to calculate, to communicate with the satellite. Okay, and imagine that that is your mobile phone and it's trying to send a signal to the satellite. So what the wave has to pass through is the atmosphere. And not all electromagnetic waves can do that. Okay, there are quite a few different layers of the atmosphere, and one of those is called the ionosphere, and some waves can't pass through that part of the atmosphere. So have a think about that one, and also you should be able to think about why it's unsuitable to use gamma rays and X-rays, even though they could pass through the atmosphere. And then number 3 is moving on to polarization, and this is something that we did in lessons. And when light is emitted from a computer screen, it's actually polarized. And so if we say that the light emitted from a screen is polarized in the vertical plane, so light emerging from the computer screen only vibrates in one plane. If we held our polarizing lens so that it only allowed light through it in the horizontal, that was vibrating in the horizontal plane, then what do you think you would see there? So I'm just giving you a clue as to what you might put for that particular question. Okay, and number 4, now both of you do chemistry, so this might be of interest to you. So sugar solution can rotate the plane of polarization of light, and all sugars seem to rotate it in the same way, to the right for example. But when you try artificial sugar, it doesn't polarize the light. And bacteria eat sugar. If you put bacteria in the artificial sugar water, when the bacteria are finished and you pass polarized light through the remaining sugar water, you'll find it turns to the left. So I've drawn this diagram to help with question 4, and there's a little bit of chemistry involved here. Now, if you look what I've drawn here, this is the structure of pentane. Now, the molecules can be arranged in a different way, and you can see that this diagram here shows an alternative structure, and this is called an isomer of pentane. Now, sugar, there are 2 forms of the same sugar molecule, and they've got exactly the same atoms, but they're arranged in a slightly different way, and these are called stereoisomers. And natural sugar contains only one form of this molecule, which rotates the plane of polarization of the light. So if we've got some light which is vibrating in the vertical plane, if it passes through natural sugar, the plane of polarization will be changed to that direction. We'll call that angle alpha. Now, artificial sugars have both types of molecules, so there's no net rotation. So in natural sugar, you'll have a molecule which rotates the plane of polarization by an angle alpha, but there'll be the other type of molecule in artificial sugar which will rotate the plane of polarization by alpha, but in the opposite direction. So the net effect of that is that there is no effect on the original polarization of the light. And the final bit about the bacteria. So the bacteria have evolved to digest only the natural right-handed sugar. So they leave behind the other left-handed type. So in the final part of the question, the bacteria are eating all the molecules that rotate the plane of polarization in that direction, and they'll only leave the molecules that allow the light to be rotated, or the plane of polarization to be rotated in this direction. So hopefully that will give you a guide in answering question 4. Quite an interesting question and quite an interesting link between physics and chemistry. And moving on to question 5. So it's been suggested that if car windscreens were polarizing and headlights were beam of polarized light, we could avoid glare without having to dip our headlights. So if you had a windscreen that polarized light, so imagine that this is the light and light vibrates in all planes. When it passed through the windscreen, it would only vibrate in the vertical plane. Now, if we had light that was only vibrating in the horizontal plane and it passed through the windscreen, the net effect would be no light would pass through the windscreen, and so you wouldn't see the headlights at all, which is quite a dangerous situation. So just a question there, a few questions to get you thinking a bit more deeply about polarization. And question 6, now we looked at 3 different situations involving interference. We did the Young's double slit experiment as part of the endorsement, and we also did a practical using diffraction gratings, and those 2 were made up practical 2 in the endorsement. And also we looked at what would happen to light if it was passed through a single slit. And I just want you to answer this question by comparing the graphs. So on the y-axis, intensity, and on the x-axis you've got distance. And for the double slit experiment, if you remember, we produced fringes whose intensity varied like that. So the intensity was the same as you moved from the middle of the screen, and the distance between the fringes was the same. So I want you to draw the graphs for the other 2 patterns and just do a comparison of what you see there. Okay, so just important point to note here. So what you have to do is draw the other 2 graphs as well and comment on the spacing of the fringes for each pattern and how the intensity varies. So with the double slit one, the intensity didn't vary as you moved from the middle of the screen, but you need to comment on how it varies for the other 2. And then questions 7, 8, 9, 10 and 11 are multi-choice questions, and I will post a solution to this, but I thought I'd leave you to have a go at these few 5 multi-choice questions at the end, without any input from me, but I will make a video later on showing the solution to these, and one or two of these are actually quite challenging, but I thought I would let you have a go at those first. So thank you, Year 12, but do email me if you've got any questions about this booklet, and if you can submit the work via Teams. It is a Word document, so you should be able to easily type into it. I will have a look and feedback on it for you. Thank you.